So, okay. So, I want to go back to the set cover problem we looked at yesterday in the problem session and showed NP hard. I want to design an approximation algorithm and do an analysis of it. Okay. So, what is the set cover problem? What is the input? Universe X and a family and what is it you want to, what is the output? You want some minimum number of subsets together cover the universe, right. So, a subfamily of smallest size okay. So, let us say so, I have this universe and this family of sets and you want to pick smallest number of sets. So, that whose union is this universe. So, what would be the optimum here? I may pick the first 3 sets for example. I could also pick 2, 4, 5. Okay, maybe any other combination will give you 4 sets. Okay, so this is the goal. You want to pick the minimum number of sets that will cover the universe. Okay. And this is a generalization of a lot of problems, including vertex cover, right. For vertex cover, the universe would be edges and the sets would be the edges incident on any vertex, and you want to pick smallest number of vertices that cover all edges. Okay. So, what would be a natural greedy algorithm? So, take the set which has the largest number of element and repeat basically every time you pick the set with the largest number of uncovered elements, right, because these elements are covered. Now, among the remaining sets, pick the one which has the largest number of uncovered elements. So, uncovered elements is my X and let us say my F prime is my solution. Pick the set in F, pick the set S such that S intersection U is the largest. And once I pick that S, I add it to my solution and what else do I have to do? U would be whatever it was minus S, because S is the set I picked, and and then repeat, right? Repeat until u is non-empty, until u is empty. Yeah. Okay, so that's a greedy algorithm. Okay. Okay, so you can come up. It's a nice exercise to come up with examples where greedy is not optimal. Greedy actually gives you ratio even more than 2. I think I added in the problem sheet. So I'm going to say exercise greedy produces greater than 2 times opt. Okay. This also means that greedy is not optimal. Okay. I mean, let's see some. I think we did even. So this generalizes vertex cover, and even for vertex cover, you probably seen examples where it does not give you optimum, right? So let's say, suppose I pick, this is my 1, 2, 3, 4, and I pick 1, 5, 2, 6. Suppose this is my family. My universe is 1, 2, 3, 4, 5, 6, 7, 8, right? What will the greedy do? It will pick actually everything. It will pick this set because this has the highest cardinality. After that, you still need to cover 5, 6, 7, 8. So, it is going to pick all of that. But if you remove this set, you still have the optimum. Okay. I mean, this is sort of a minimality check you can do, because after you produce the solution, you can run through and check whether any set is required and get rid of it. That is one way to deal with this problem, but there are more involved examples where greedy can be way off from optimum. Okay. So, what I am going to show you is that the solution produced is, it has an interesting approximation ratio. It is a natural log of n approximation ratio. So, what we will show that greedy solution, by this I mean for any input. Okay. So, this is at most ME times opt. Okay, what is this H function? H of I is a harmonic function. Okay. So, H stands for harmonic, and this is nothing but 1 plus half plus 1/3 plus, actually this there is a plus 1, I think. No, it is H. And asymptotically, anybody knows how this function grows? Okay, this is an interesting exercise. Yeah. Yeah, it's a natural log function. Yeah. So, this is, so let me just give this as an exercise. Yes. So, let's do this at least one more step. What he is saying is, suppose I draw the function y equal to 1 over x. How does it look like? It's like a hyperbola kind of thing, right? So, y equal to 1 over x would look like this, right. So, for 1 it will be 1, for 2 it will be half, for 3 it will be 1/3, and the function will look like this. Okay. Now, what is the sum I am interested in? I am interested in 1 plus half plus 1/3 plus so on and so forth. So, yeah. So let's now it's nice. Okay, so it's natural log plus 1. So let me ignore the 1 here. So what is the area of this region? Half. Everybody see that? What is the area of this region? I mean, my drawing does not reflect the correct proportion, but what is the area of this region? Well, this is 1 and this is 1/3, right. So, sorry, I should have said, yeah, this region, this rectangle is 1/3, right, and if you take this rectangle, this is 1/4. So, my interest, what am I looking for? I want half plus 1/3. So, it's basically area of this region plus this region plus this region plus this region is what I am interested in, which is upper bounded by area under this curve from 1 to n. And what is the area under the curve? The integral. If you do integral 1 over x, it is natural log of x, right. So this is half plus 1/3 plus 1/4, but I also have to add 1. So, this quantity is upper bounded by. Okay. So, I more or less given the proof, but it is a very cute geometric proof. So, you can draw the curve and see what is it you are interested in. These are rectangles, area of these rectangles is what I am interested in. It is upper bounded by the area under the curve, which is the integral of the curve. Okay. So, what am I claiming? That the solution produced by the set cover greedy algorithm is at most natural log of whatever the maximum size of these sets is. So, if it is as bad as n, then it is natural log of n plus 1. Okay. So, it is not very easy, there are lots of different proofs. I will try and give one proof which is there in Carmen. So, what we are going to do is the following. So, the claim, yeah, okay. So, the claim is this. Okay. So, let S1, S2, SL be the sets picked by the greedy algorithm. The greedy algorithm picked some L sets, and I want to show that this L is upper bounded by this, right. The number of sets I have produced is upper bounded by this. Okay. I mean, where does log and harmonic come in? Well, I do not think, well, I mean, if you experience it, you might get some intuition out of it, but otherwise at this point it will be some calculations basically. Okay. So, each set is covering some new elements, right. My greedy algorithm picked S1 first, and then it picked S2, S3 and some SL, and it covered all the elements, and each new set is covering some new elements, right. Otherwise, why would I pick that? So, now I am going to, so each set costs 1 unit for my solution, right. That is a totally L units. So, that 1 unit I am going to distribute to the elements it is covering. Okay, so, some sort of a weight distribution, and I am going to measure it that way, right. So, let x be in my universe be covered first by the set Si, right, because my S1, S2, SL cover my entire universe. I pick some element of my set, it is covered by one of the sets, maybe by many sets, right. Let us pick the first set covered by x, okay, and I am going to associate a cost with that element is equal to 1 by cardinality of Si minus S1 union S2 union Si minus 1. Okay. So, X is in this set, right? X is in Si, but not in any of them, because this is the first set covering X. X is in Si, but not in any of the other sets. So, there may be many sets, many elements that are covered by Si, but not others. All the elements distribute this cost. So, Si has a cost of 1, because I am picking that set. That cost I am going to distribute it to all elements first covered by that set. Okay. Now, can you tell me what is L? So, is this clear? I have given a cost to each element of the universe. Okay. I have just now, what is L? L is the solution size, but can you say it in terms of the costs? So, L summation of all C x, yeah, the cost, right, summation C x x in x. Agreed, because this set comes and covers some 5 elements. Okay. So, I have to take a cost of 1 for this set. What do I do? The 5 elements this is covering, I am going to give a cost of 1 by 5 for each of them. So, when I add them all, it gives you 1. So, I am just distributing the cost of this sets to the elements. Okay. If you understand it, I think more or less everything else will be pretty easy. So, this is the the solution produced by cost of the solution is equal to summation C x. Okay. So, let C star be an optimum set cover. Okay. C star is a family of sets. So, C star will look like, oh, this set followed by this set and this set. Now, suppose I add the cost of elements in each set, summation C x x in S over all S in C star. What can you say? So, each element has a cost, and this C star is a set cover. So, it will cover all elements. It will be this. Okay. Okay, right direction, but not completely correct. It will be exactly L. So, these sets are not disjoint, remember, right. So, the same x may appear here, it may appear here, it may appear here. So, this is less than or equal to summation S in C star, summation x in S C x. Okay. Now, what we will show, this is the big claim, we will spend 5-10 minutes on this, that for any S in my family, summation C x x in S is less than or equal to the harmonic sum of this. Okay. So, I am going to prove this claim. We will show that you go to any set in your family and I assign these costs by the way the greedy algorithm picked elements, picked my sets. I will argue that for any set the summation C x is at most the harmonic sum of this. Okay. We will come to that. But if I prove this, what happens? Then this thing is upper bounded by H of S, right, after I prove this claim. And this is upper bounded by H of max of S. So, this C, okay, let me write again. So, L is equal to summation C x x in x, which is less than or equal to summation S in C star x in S C x, which is less than or equal to summation S in C star H of S by the claim, which we will prove. which is less than or equal to summation S in C star H of max of S. S is in family F itself, does not matter. Okay. This is equal to cardinality of C star into H of max of cardinality. Is the sequence of steps clear? From here to here is the big claim which I am yet to prove. After that I said, well, this is the harmonic sum. Remember 1 plus half plus 1/3 up to 1 by n. When I am upper bounding by max of this, right. So, now this quantity is independent of this particular S. So, it is appearing C star times. So, I took C star out, and this is what we wanted to show, right, because the solution size what I have is at most this is the opt times the harmonic of max S. This is what we wanted to show. Okay. So, I am done if I prove this claim. Okay. So, this is more or less some calculations, something like 1 page. So, proof of claim. What is the claim? Summation C x x in S is at most the harmonic. So, let us pick one set S, may or may not be in my solution, but it is in the family, right, for any set. And remember, my solution is some S1, S2 up to some SL is what the greedy algorithm produced, and that is what gave me the cost, right. Okay. So, let u naught be the size of S and u I equal to size of S I minus S minus S 1 union S 2 union S I. So, I have picked one set S. Okay. So, let us S is one set in my family, and I want to prove that for that set, for any set, this quantity is true, right. So, S has some elements, and each element gets some cost based on these greedy choices. So, let us say u naught is the size of S and u 1 would be S I minus 1 really. So, these elements are covered by these SIs, right. Okay. So, let us say this set of elements are covered by S 1, maybe these are covered by S 2 and so on, and maybe even you do not even have to go up to L to cover this set. This set is so special that maybe some S k covered this, and up to S k everybody is covered here for this particular set S. Okay. So, I am calling u I, let me use the exact notation. Okay, so I think it is S minus S I. Oh, u I is a set of uncovered elements. Okay, set of uncovered elements of S after picking S 1 to S I. Okay, so after you picked S 1, this would be the u 1 size of u 1, and after you picked S 2, this will be u 2 and so on. So, clearly u I is less than or equal to u I minus 1, because after you pick more elements, the number of uncovered elements is going to decrease. May decrease, it may remain the same, but it is not going to increase. because these UIs are associated with the cost. So, what is summation Cx x in S is exactly summation I equal to 1 to k ui minus 1 minus ui. These are the so many elements covered by my new set S, and what is the cost? This will be the way we have assigned it, S 1 union S I minus 1. Okay. Then with some algebra, basically that is it. So, I am adding the cost of all elements in this set. Let us see what the cost would be. So, whatever S 2 is covering, remember the elements of S 2, whatever is covering is S 2 minus S 1 is the cost of each of those elements. So, those elements of S covered first by S 2 will get a cost of this much, and how many elements are there? That will be something like this. So, this sum is exactly summation Cx. Clear? This is just the way we assign the cost. So many elements will get this cost, next so many elements will get this cost, and so on. Okay. But okay, so now I want to show, I want to claim that this is less than or equal to right. Okay. So now look at S I minus S 1 union S I minus 1 and S minus S 1 union S I minus 1, right. What can you say about, okay, let me write this here. So, there is cardinality of S minus S 1 union S 2 union S I minus 1, and this is exactly U I minus 1 by my definition, and then there is cardinality of S I minus S 1 union S 2 union S I minus 1, which is bigger between these two terms. S is some arbitrary set, S I is the ith set picked by the algorithm. So, which of these two would be bigger? You are saying this it will be like this?
Because Si minus that is the number of uncovered elements just by that set.
Yeah.
The number of elements that are just covered by that set right now, and S minus that I think is the total number of uncovered elements so far.
For S only, this is only still we are looking at S. Okay. What did the greedy algorithm do at this after picking S 1 to S I minus 1 is it is picking the set which has the maximum number of uncovered elements at that point. So, S I minus this is larger than this because algorithm picked S I. The algorithm picked S I because the number of uncovered elements, I mean if you compare these two elements, if this were larger, algorithm would have picked this. Since algorithm picked this, this quantity is this. So, 1 by this would be less than or equal to 1 by ui minus 1. Okay. So, summation Cx x in S is equal to summation ui minus 1 minus ui I equal to 1 to k 1 by ui minus 1. So, all I did was I replaced this quantity by ui minus 1. Since this is bigger, 1 by that is smaller. Okay. Now, it's just some, there is some harmonic coming here, you can already start seeing. So, this is 1 to k summation j equal to ui plus 1 to ui minus 1 1 by ui minus 1. So many times 1 by ui minus 1. So, I am just going to write this. This is less than or equal to 1 to k one by j, and this is equal to because UK is 0. Okay, so this is some calculation, but I mean, I don't expect you to just get everything, but the important key idea is somehow distributing the cost from the set to the elements gets you handle to argue something about it. Okay, so this is from CLRS. So if you miss something, you can go and verify it there. Let me just make one corollary here, and I'll complete. Okay, so here is the thing we proved. What we proved is the solution produced by the greedy is at most harmonic of the maximum of the cardinality of the sets times opt. So the ratio would be this. Okay. And this, since vertex cover is a special case of set cover, even for vertex cover this ratio applies, but maybe you can get something better for vertex cover because it is a special case, but the answer is no. There are examples where there are some tight, log n is the greedy algorithm can produce as bad as a log n times optimum. But suppose the graph is, let us say, a cubic graph. Okay. The max degree of every vertex is 3. It turns out vertex cover is NP hard even in such a special class of graphs. Now, if I apply the greedy algorithm for minimum vertex cover there, what kind of approximation ratio would I get? It is here. If the graph is cubic, max degree is 3, and if I model it as a set cover, right, it's we already saw you can model it as a set cover. You want to cover all the edges, that is a universe, and each set would be the number of edges incident, the set of edges incident on that vertex. So, and if I apply the greedy algorithm and apply this analysis, what would be the approximation ratio? Less than 2. More precisely, it will be 1.8. How did you get 1.8? It's basically, what is the size of these sets? Remember, in your modeling of set cover, what are the sets? Edges incident on a vertex. How many edges are incident on a vertex? 3. So, max of this cardinality would be 3. So, we are talking the approximation ratio is harmonic in 3, which is 1 plus half plus 1/3, which is what? 1.8. Okay, I believe you. So, it is less than 2. But I think there are even better approximation algorithms. So, I would just want to write corollary is that in cubic graphs, where max degree is at most is actually 3, because otherwise it is Poisson time solvable. Greedy has an approximation ratio of harmonic of 3, because the set sizes are 3, which is equal to 1 plus half plus 1/3. So, it is 11 by 6, right. So, it is better than 2. For general graphs, we had, the matching algorithm gave us a 2 approximation, but if your graph is cubic, you get better approximation. The standard nice greedy algorithm gives you better than 2, but I think there are even better approximation algorithms. Okay, so I think I will end my discussion on approximation algorithms. We saw approximation algorithms with ratio. No, I will do one more tomorrow maybe, okay, because we have not seen any maximization problem. We have been seeing a lot of minimization problem. So, I will do one more lecture on approximation tomorrow, at least one more. So, we have seen 2 1.5 for okay, we've seen approx ratio 2 for minimum vertex cover in general graphs, 1.5 for metric TSP, and also for make span today we saw, right. And log n for set cover, and something like 11/6 for cubic vertex cover. So, the approximation ratios come in various possibilities, and I also mentioned to you, we did not see and we may not see, that there are problems for which you can get arbitrarily close to 1 plus epsilon approximation algorithm, and what you pay for is in terms of the running time. Okay. There is actually a notion of hardness of approximation also, interestingly, just like NP hardness theory gives you, there are certain problems which cannot be solved in polynomial time. There are, under some assumptions, you can show that, for example, set cover cannot be approximated better than log n.